Next example is what I can call Monty Hall fallacy. So, the first example you saw was this, let's call it example 1. Next is example 2. So, you can call this Monty Hall problem or Monty Hall fallacy. You will see why it's a fallacy. It's a very interesting idea for a game show. So, from Monty Hall's TV show called Let's Make a Deal. Which ran successfully in 1960s. So, in one of these shows, one of these episodes, the game was that Monty Hall, being the host, he has on the stage there are 3 doors. One hides a car, the other 2 hide goats, and the player has to pick one of the doors, and then there is a protocol. Okay, so let us describe what the player has to do. So, there are 3 closed doors in the show. So, one hides a car and the other 2 have goats. Okay. So, you are asked to pick one, to pick a door without opening it. So, the host Monty to confuse you, what the host what Monty does is he opens. So, now there are 2 other doors, right? One you have chosen, the 2 remain. So, clearly out of those 2, one, at least one has a goat, and Monty knows it. So, he opens that door and shows the goat. So, the host Monty opens one of the 2 doors. To reveal a goat. Okay, so now you have one door picked, and there is another door that is left unpicked and unopened. The question is, looking at the goat, should you swap your choice? Should you change your choice or not? That's the question. So, should you switch your door choice with the third one? Should you stick to your ground or should you flip? Okay, that's the tough question for you. Now, it may seem that this new information that Monty has shown you presence of a goat was known to everybody. So what's the point of switching, right? You can as well stay your ground, and that is where the fallacy is, okay, which Bayes' theorem will resolve mathematically. Since Monty hasn't given any new info, you shouldn't change your choice. Okay, but if you think this, then you are very wrong. Okay, so let us do the analysis. So let the doors be labeled naturally 1, 2, 3 with door 1 being your pick and door 2 being Monty's pick. Okay, so this is post facto labeling of doors. The one you picked is 1, Monty picked second, third is unpicked and closed. So we can assume that since you had picked your door randomly without any information, so the probability of the car being behind door 1 is 1/3, right? And before Monty picked door 2, actually probability of car being behind any of these was 1/3. So in fact, let me first define the events. Or yeah, let me first define the events. So the events are so DI is the event the car is behind door I. And M2 is the event that Monty opens. Door 2. And these are already conditioned on door 1 being picked. Okay, so the event definition happens after you have picked door 1. So basically that sets the scenario mathematically. So you have picked door 1 and after that Monty has two choices, either to pick door 2 or door 3. He happens to pick door 2 with probability half, and just conditioned on you picking door 1, the probability of car being behind door I, that's 1/3, right, for all these I's, because no information has been released to the public by you just picking door 1. So you can assume it to be uniformly distributed, so that's 1/3 probability. So probability DI is 1/3 for all I, and probability of Monty picking the second door is half, And now what do you want? So you are interested in evaluating the probability that that door 1 is good. Given that Monty opened door 2. Right, this is what you are interested in, which is symbolically it is probability of uh, event D1 given M2, right, which by Bayes theorem is probability of D1 times probability of M2 given D1 divided by probability of M2, which is, so let us write this down. Probability of D1 is 1/3 times M2 given D1. M2 given D1 is half, and so I should call this M2 given D1. If door 1 has the car, yes, so let me correct something here. So given that first door has the car, second and third doors, both of them have goats. So Monty could pick any of those two. Okay, so that probability is half. But probability of just without any extra information, probability that Monty will pick the second door, that is not clear. Okay, that is not at all clear. You have to, we'll do that actually using the partition formula. So let me continue with that. Right, so probability of D1 is 1/3 and M2 by D1, M2 given D1 is half, and then I will break up probability of M2 like this. I will have this, which is with respect to D1, then I have with respect to D2, and then I have with respect to D3. Okay. So I hope this is clear. This is because I am using the partition D1 union D2 union D3, because the car can only be, it's a unique, it can only be in one of the doors. So this is an actual partition of the sample space, and then M2 I am conditioning on these three, and then I have the partition formula. So let us now work this out. So I have 1/6 divided by 1/6 plus probability of D2 is of course 1/3. Now if the car is in door 2, then Monty will never pick that door because Monty has to reveal the goat, right? So this probability is 0. Now next is probability of D3 is 1/3. Without any extra information, car could have been in the third door. It could have been in any of the doors equally. But once the car is in the third door, Monty is forced to pick the second door. Okay, there is no choice. So this probability is 1. Conditional probability is 1. Now what do you get? So 1/6 divided by half, right, which is 1/3. So you see that the probability of door 1 being good is quite low. It's much less than 50%. Right, which means that you will actually have an advantage if you change your decision. So this means that you should change your decision. So you should switch your door. right? So that's the amazing consequence of Bayes formula, which was completely not clear before we started this analysis, right? So just by Monty showing you that door 2 has a goat puts more probability or puts more likelihood on door 3 having the car, not door 1. Okay, the probability is kind of biased towards door 3. So this is called the Monty Hall fallacy or Monty Hall problem. And with this, let me go to a new property related to a probability distribution function, which is random variables. So recall that we defined the probability map on subsets, collection of subset called E of omega. So what was E? E was this sigma algebra, and omega was sample space. So point being that probability map was defined on the subsets, right, in the most general form. But sometimes, in fact, many times in experiments, we want the sample space elements to be numerical values. We are actually interested in the numbers, not just subsets. But many a times we need numerical values associated to the outcomes of the experiment. For example, when you toss many coins, what is the number of heads, right? So head is being seen as 1, tail is being seen as 0. So number of heads in n tosses, or payout of a lottery. Right? In any of the casino games, you will be interested in the payout. So which is a number, right? You don't care about subsets, you actually care about these numerical values. So we have to expand our definition of probability distribution to make sense of numbers inside omega. So let's do that. So random variable is a function x from omega to reals, that is it maps element omega to x omega, and this is a real valued random variable. We will only be interested in real valued random variables. So it is nothing but a function from sample space to real numbers, and the value is x of omega for every omega. That's all. But then it start giving you many related things, new things, like we can talk about events x being equal to a value. Okay, so this is the event that, so we are interested in those elements in the sample space that evaluate to this number x. That's an event. This real number x. So this is the subset of those omegas in the sample space which evaluate to this element, this number x, little x under big X function. We also can call this x inverse of x. So once you have this event defined, you can define, you can extend now the probability distribution function for this, which will be big X equal to small x. Probability is sum of p omega, where omega is in the pre-image of little x. Okay, all these omegas that are relevant, just sum up their probability. Yeah, so now there might be some issues when you go to infinity. So for that, I will just say that we'll consider only those x that have a countable range. Okay, so range meaning the values that x takes overall, the function x takes overall, that is a countable set. It cannot be, we don't allow whole real number set, but it's something like integers or natural numbers or rational numbers or sets that are in bijection with this. So these are called, then x is called discrete random variable. Okay, so we are only interested in these discrete random variables, and then hopefully this sigma, the sum of probability, will make sense, but we will not go too much into that right now. And this has a name, so this is called this action of p on x equal to little x. This is called probability mass function of a random variable. Okay, so mass function because it is telling you how this random variable big X is distributed. Okay, so for a particular value small x, what is the chance that it is equal to this? This is called a probability mass function, and this we have defined. Okay. Now clearly this random variable given a probability distribution function, there may be many possibilities to define big X. Okay, just like there are many p possible. There are many x possible for omega p. Okay, so this given omega and e, yeah, maybe I should call this e instead of omega. So given a sigma algebra, there are many ways to define probability function p. And even if you have defined it, once you have defined it, there are many ways to define x, the random variable. Okay, these things are not uniquely defined. Okay, so shall we see an example? Okay, let's see a quick example. So say a coin is tossed 10 times. So what is the probability of getting k heads? Okay, we are interested in this question. So in this case, omega is head or tail 10 times. So this Cartesian product is the sample space. Probability of head, probability of tail is obviously half. And what is the random variable? So you want to see h as 1, t as 0. So it sends little omega to little omega is a sample space element, right? So this is a string of 10 head or tails. So just the number of heads in omega. Okay, that is the random variable for every instance of the experiment. And now what is the probability of x being k? So this is you look at basically the places where head appears, right? So let S be a subset of 1 to 10 k sized. So probability that H happens in locations S times the probability of x being k. Given H is in locations S, which is what? Well, once S locations or head, so it means that x is k, so that probability is 1. And what is the probability that H is present in these locations? Well, that probability is just 1 over 2 raised to for the head, and the remaining 10 minus size of S, right, which is, so what you get is number of subsets, that's 10 choose k times 1 over 2 raised to 10. Okay, so that's the mass distribution function. That is the mass function in this experiment. Okay.